Hello, my name is Guilherme de Souza. I'm a fourth-year PhD at the University of Maryland. I work with Professor Christopher Jarzynski on topics that range between statistical physics, quantum mechanics, and in particular, that project that we'll be doing here is related to quantum control, and that really started, during this project funded by FQxI, Information as Fuel. And the results that I will be presenting here were done in collaboration with, theoretical groups at the University of Lund. Under the supervision of Peter Samuelson and Patrick Potts at the University of Basel. So the idea that we try to create here is that we are trying to understand what happens when you're measuring your quantum system, and by measuring you're gathering some information, you want to process that information and you want to apply some feedback because you want to be able to extract some useful information, so do some useful work. So that's the overall goal. So what we have done here is that using the formalism of weak measurements that allows you to model your system when you're continuously measuring, so you're not doing a single shot measurement in your quantum system, you're gathering information over a long period of time. So you're using this very nice formalism of weak measurements. So what we have done here on top of that is consider that a real experiment actually has a finite bandwidth when it comes to the information processing. So that's the two most important ingredients that we added on top of the stochastic Schrödinger equation to derive our very nice framework. So we have the how fast we process the information and how much information we gain. And the master equation that we derived is called the quantum Fokker-Planck master equation. It contains the usual Schrödinger terms and back action terms, but it also contains some dynamics on the measurement signal, and that dynamics on the measurement signal that actually gives the right information about how we're processing information, how we're gathering information, and how we can use that information as a fuel to actually do some very interesting quantum protocols and quantum, in general, quantum feedback. So what I have done here as a nice step forward in the project was to apply our framework to a particular example, so we can get some more intuition on how is this working. So the particular system that I chose was a quantum harmonic oscillator, where I'm performing both position and momentum measurement. And after the measurement, I do some processing, which basically consists of applying some low-pass filter. And based on that processing, I move the position of the trap in such a way that I try to keep the particle in the bottom of the trap in a way to cool down the particle, maybe all the way to the ground state. And what I was able to do here was to derive some very nice analytical results using the quantum Fokker-Planck master equation. And the analytical results for the energy in the long time limit energy was that it actually depends on the trade-off of how much information I get and how fast I process that information. So it's nice to get mathematical results that actually are in line with our intuition when deriving this very nice framework. So, and by actually tuning how fast you process the information with how much information you're getting per unit of second, you actually can cool down this harmonic oscillator system all the way to its ground state. And actually, even better, you can do that arbitrarily fast by tuning your measurement bandwidth. Another project that we are kind of doing as a natural connection and natural next step from the formalism that we derived is to investigate what happens if in your experimental setup you have more than one source of information bottleneck or information processing. And that information bottleneck basically creates a natural bandwidth for each component of your experiment. So what happens if instead of just a single finite measurement bandwidth, we have multiple, maybe 2 or 3. So what happens is that we investigated the same system, but now in this more generic setup, and we're even again able to derive some nice analytical results. And in this much larger parameter space, we can even help the experimentalists to choose the right knobs to turn such that they can cool down the particle to the best they can given their experimental constraints. So for example, here we can show some very nice diagrams where the experimentalists could choose to apply the feedback using a single layer of filtering, 2 layers of filtering, 3 layers of filtering, and so on. So this is a very nice extension, and overall this project has still a lot of to grow. So the next natural steps would be to investigate more from a more theoretical information perspective, what's actually happening in terms of information processing, what is the entropy of how much information I'm processing, and maybe even have some experimental verification of that, and more realistic scenarios where we can process the information more closely on how the experimentalists are actually doing the experiments.